Okay. Welcome to lecture 12 of the PCP course. We're going to be entering the last module of this course, and where we will see some of the most recent happenings in the area of PCPs. In particular, we will see an overview of what's called today the 2-to-2 games theorem, which was part of a fantastic collaborated effort that went in the last 4-5 years towards trying to prove the unique games conjecture. So this it's going to be, I'm going to do a series of lectures, possibly 3 or 4 lectures, depending on how much time it will take. So today's lecture will sort of do an overview of this entire, what the 2-to-2 theorem is, why is it a useful theorem, how do we go about proving it, and such stuff. And then the individual parts, we'll try to prove each part of this over the next few lectures. So let's see even before the 2-to-2 theorem, let's recall what the unique games. Recall the unique games problem. So this usual label cover, instance phi, which has a bipartite graph, UVE, a label set sigma, and set of permitting phi e is from sigma cross sigma for every e. And the value of the instance, particular instance, is the max over all assignments to the vertices. We are going from union B to sigma, such that probability when you pick a random edge UV, phi E of AU comma EB. And gap CS for 0 less than S, less than equal to S, less than C, less than equal to 1. Gap CS label cover, exactly the S instances are those phi for which val phi is greater than or equal to C. And then no instances are those phi for which val phi is less than or equal to S. And the classic entity and the PCP theorem plus parallel repetition gave us the following. That is for all epsilon 0, 1, there exists sigma, and the size of sigma is typically poly 1 over epsilon, such that gap 1 epsilon LC with sigma is NP100. And then we saw that this was an amazing theorem. This led to proving several hardness, optimal hardness. Some of them did not know how to prove. This was not strong enough. So in this one code suggested a strengthening of above, and he said, let's look at ULC instances. These are instances where phi E sigma cross sigma is a matching. That is, if you look at this, I'm focusing on a particular E, and I'm looking at which are the accepting edges, which are the accept not edges, which are the accepting this ones. This is like a matching. That's how it looks like. And the unique games conjecture of court is basically the fact that for all epsilon, there exists a sigma such that gap 1 minus epsilon ULC of sigma is NP hard.
Actually, UGC is not comparable to the projective flavor forward.
What?
UGC is actually not comparable to the previous.
In the sense?
You have 1 minus epsilon in UGC.
Yes, yeah, but it's you mean to say it's not a strengthening of the above because of that? Yes. So the next one which I state will be it's not a strengthening. It's not a strengthening of the above state. Certainly, it's not a strengthening because of 1 minus epsilon.
So you want sigma here to not be very large.
So here at this point of time, I'm only looking at for constant epsilon, constant sigma. I don't care what the function of.
So you don't care about the dependence.
I don't care about the dependence. Yeah.
And that is because in those detailed tests, the dimension is the bounds are independent of sigma in majority cases.
Yeah, those results are the
So that is why we care.
yeah. If over there, eventually later on, I would like to understand how small I want to get it, then I might want to look at this. But right now, those like vertex cover and majority and max cut, just care only for an arbitrary, any dependence is fine. Okay. So since quote conjecture, suppose this is a potential hypothesis, there have been several efforts both to prove this. There have been three sorts of efforts. One is the efforts which we saw, see what are the consequences of UG. What does UG? And that's what we saw, vertex cover, we saw max cut. There have been efforts trying to prove UG, and there have been efforts trying to refute UG. There have been three sets of efforts. Prove UG. UG happens to be one of these strange problems for which we actually, typically when a problem is hard, you not only are able to, like SAT, but SAT is a hard problem. You're able to use the hardness of SAT to prove the hardness of other things. That's what we have done so far with UG. But you're also been able to prove the hardness of SAT, assuming the hardness of some other problem. You're able to show this. UG is one such problem which is sitting out there, for which I don't know what implies the hardness of UG. So it's sort of a, we don't know of a natural problem that will imply it. Though there have been efforts recently, since this one, there's one problem for which we know, which is called small set expansion. Small set expansion is a problem which actually happens to be equivalent to UG. I'll not go into the definition of small set expansion. That's the only problem for which we have a reduction from that problem to UG rather than from UG. So in fact, you want to prove UG, either you give a reduction all the way from SAT to this one or to some other problem. So that's one. The other sort of this one. So okay, this is from the trying to prove UG. What about from refuting UG? What are the efforts that have been going on? There have been multiple sort of efforts that have been done. One is actually come up with semi-definite SDPs. Typically, how do you solve these CSPs? CSPs are you write a semi-definite program like for max cut, Gomez-Williams wrote it. Write an SDP and see if you can solve UG like instance. And here came actually the strongest sort of reason why people believed UG was false is Eventually, this came toward due to a work of Aurora Barak and Steurer. Efforts to refute UGC to ABS. Aurora Barak and Steurer. Well, gave an algorithm that runs. It didn't refute UG, but it ran in time 2 to the n to the epsilon prime, such that it did the following. On 1 minus epsilon satisfiable ULC instances, it found an assignment it found a 3/4 satisfying assignment. So you knew that UG was solvable on 99.99 fraction of the instance given to you is actually solvable on 99.99 fraction of the edges. There is one assignment. It finds an assignment that satisfies 75% of the edges. And similarly, it also did the other way. That is, on half satisfiable instances, it found a epsilon satisfying assignment. Notice if they had given a polynomial time algorithm, this would have refuted UG. They didn't give a polynomial time algorithm. They gave a 2 to the n to the epsilon prime algorithm, and epsilon prime went to 0 as epsilon went to 0.
Then doesn't that mean UGC and ETH cannot be simultaneously?
Yeah, so the question is, the moment this thing of Aurora Barak Steurer came, what does that mean? So this typically means, so this what UG, so question is, you want to say UG is NP hard. What does it mean to say UG is NP hard? That's a conjecture. That means there's a poly time reduction. Now you can ask, what is the running time of that reduction? Is that reduction a fixed polynomial time, or is the polynomial time growing as a function of this epsilon? The exponent growing. There's nothing right now, the way quotes the UGB stated it, the reduction could run in time which is poly in n to the 1 over epsilon. Because I'm asking it for every fixed epsilon, I'm asking this. And that doesn't refute this issue at all. So all the ETH thing will go out. The reduction runs in times 2 to the n to the 1. It runs in time n to the 1 over epsilon. But this was not a usual feature of NP-hard problem. Whenever we have problem was NP-hard, typically we have found linear time reduction. So our usual textbook reductions for vertex cover, independent set, this one, when you proved NP-hardness, they were actually just order n. Reduction from SAT to the various problems. The textbook reductions were all order n. Of course, you could say this. This theorem was not. This was not a linear time reduction. In fact, parallel repetition blew it up. It took n to the log 1 over delta. The reduction ran in time. If you wanted to get 1 epsilon, the reduction was running in time n to the power log 1 over epsilon. So this is already not such a feature. But though I've stated this way, there's a result due to Moshkowitz and Raz who actually show that this can be made nearly linear.
Or is that?
So let's say, so I just want to say, so the MR theorem, the M Moskowitz and Ross, states that for all, so this one, so just to say, the under order n to the log 1 over epsilon time reductions. What do MR prove? For all epsilon, there exists an alphabet sigma. Sigma is unfortunately not as small as, it's not poly in 1 over epsilon, it's exp in 1 over epsilon in this case. Such that gap 1 epsilon label cover is NP hard under order n to the plus some little o1 times poly 1 over epsilon time reductions. And in fact, we almost saw full proof of this last time. So you remember we did a proof of the two query PCP when epsilon was subconstant. Basically, this is what is going to give you epsilon. This is the thing which gives you epsilon subconstant. You can take epsilon to subconstant. And the proof was essentially the proof which we saw basically gave us the proof which we saw using the new other style of composition.
The subspace query.
Yeah, that would have given you this. That would have given this, except the way I did in class, it would have given you n cube. This one, it was fixed polynomial, it's not linear, it's fixed polynomial. You could de-randomize that and actually get order n also. So basically, the proof we did in class gives you order n cube. Was in the last lecture. And
so what are some of the other examples that we are talking about the rest of expansion and like natural ones?
So the natural ones appear in the world of FPT. The FPT, the fixed parameter tractable things, they appear, but not in the ones which we studied. And somehow this fact that everything that we knew were NP hard, except for example, this was not, but now this has also been made NP hard under nearly linear time reduction due to the reduction of Moskowitz-Ras. Sort of seems to suggest that if this is sort of some belief in the word, if something is NP hard, it's actually NP hard under nearly linear time reduction. This need not be true at all. There's nothing in the definition that warrants this. And so, but it led people to believe that possibly the existence of the Aurora Barak-Steurer theorem suggests that possibly UG is not NP hard. That's one thing for which. The other thing is typically a problem is hard. What we have been successful is we have been able to successfully generate instances on random instances on which we don't know how any efficient algorithm could solve it. That is, we can come up with a distribution of instances of the random instances of the problem for which every current known algorithm fails. UG is one of these problems for which we have been unable to do this till today.
The random instances are easy, or the
random instances are all easy. The random instances, the underlying graph tends to be an expander. On an expanding graph, UG is actually easy.
so system becomes unpredictable.
The system, in the sense that if it were 1 minus epsilon satisfiable, it's easy to produce a satisfying assignment over there.
So you just like locally do some assignment.
And so expanding the local things propagate globally, therefore it just works out. All of these things. And in fact, that's what goes into The aurora borealis spider.
Propagation method or any one of its propagation method?
Propagation. Question is how much do you lose in this propagation? Expanding grass, the propagation is much better off, and that's what. So what's this? So UG is so the reasons I'm talking about reasons people believe UG is possibly not hard is one, there's the existence of the aurora borealis spider algorithm. The other is it was a place where we were not able till date, we haven't been able to come up with a distribution of hard instances. These are all our inability.
Well, we have search for set.
Yeah, SAT we do have.
Which case set?
Random SAT is
It depends on the variable, like what is the number of clauses.
So if you choose the number of clauses to be linear in the number of variables, this is a setting for which.
Like you get threshold values.
Abhinay.
In a threshold value.
So in the around the which threshold where it happens, we don't know how to do this. These are in fact believed to be hard instances for random SAT, and even the current all the existing SAT solvers all just fail on this. What solvers fail? Another one is inability to find a distribution of hard instances for each. So these are proposed as things for which possibly and probably they said that suggest actually there is UG is easy, and that's why we're not being able to ever lay our hands on. Okay, so because of these two factors, because in some sense the combination of these three things, the Moshkowitz-Raz result, the aurora borealis algorithm, and this inability, these three things led people to sort of question whether UG is possibly true or not, or there's a chance that UG might be false. But what happened in the remarkable sequence of results due to 4 papers, Fort, Minzer, Safra, KMS1, Dinur, Fort, Kindler, Minzer, Safra, BKKMS 1, then DKKMS 2, and KMS 2. Essentially 5 authors over a set of 4 papers together showed that a variant. Actually, let me read out the paper here. These are all not too long. Variant and paper. This is 2017. These two are 2018. And this is 2019. But also 2018. That won't happen fairly quick. I think this is Fox 2017, these are Stock 2018, and this is Fox 2018. So period of 1.5 years. They showed that a variant of UG is actually empty hard. And that's going to be the focus of this one. And what's the variant? It's what we are going to call the 2-to-2 games. Hmm? So what are 2 to 2 games? Now it's just changing what the pi is. So the pi in the previous case, the sigma cross sigma 0, 1. It's basically something of the following type. I'm going to draw sigma sigma. It's a very specific case. It looks like for every possible assignment to one side, there are 2 possible assignments to the other side that satisfy this. Looks like that.
The graph is the one of these cycles.
Huh?
And the graph is like the one of these cycles.
So strictly speaking, it's a bunch of cycles. In fact, even more, the bunch of the specific examples which they prove NP hardness is a bunch of 4 cycles. It's exactly like that.
Sorry, what is 2 to 2 here? So for every assignment.
For every, this is on the graph, this is, I'm drawing a particular pi. This is not the bipartite label cover instance. I'm taking a particular edge and I'm looking at which sigma cross sigma are actually the satisfying instances. Previously noticed in the UG, this was a matching over there. For every guy here, there's 1. So for every guy here, there are 2 here that are satisfied. Therefore, if you draw this graph, every vertex has degree 2.
And this is also true for the right.
Yeah, it's 2 to 2. Those are the 2 2s. It's 2 to 2, it's 2 from either end. So in the other sense, if you draw this graph, this is a union of cycles, in particular union of even cycles. I'm going to state it even more. That's what the 2 to 2 theorem says. Actually, the construction which we'll see, which will actually give you a union of 4 cycles. Okay, that is the graph of each constraint. Graph of each constraint. Graph of each constraint by E is a union of even cycles. But of course, the picture I drew is even more specific than that. So we will actually explicitly say what I'm going to show a particular type of 2 to 2 problems are going to be NP hard. And so we're going to talk about a 2 to 2. The L is going to be some integer. 2 to 2 games F2L. So what is this? This is going to be the instance P is going to have n variables, x1, x2, xn, and each of the variables take values in F2 to the n. So the alphabet, the underlying alphabet, think of it as L-bit alphabet. One. There are m constraints. C1, C2, Cm. And where each constraint is of the each constraint C is of the form it's going to involve 2 variables xi and xj, and it's going to put ti tj is in P1 or P2, where Ti, Tj are invertible F L cross L matrices. So this is basically Pi xi is basically another vector of length L. This is another vector of length L, and you're taking the addition of those of them, with pair element wise addition, that should be one of two vectors, v1 and v2, and v1, v2 are also elements of F2.
So Ti does not depend on C.
Huh?
Ti does not depend on C.
Each constraint C is of this form Ti, Xi, Tj, Xj. So the constraint is specified by Ti, Tj, v1, v2.
So does this Ti depend only on Xi or it does different C remain the same?
No. Ti different C's they have different. So every C tells you which two variables, which two matrices, which two vectors. It comes a constraint is specified. A constraint C is specified. More specifically, constraint C is actually given by I, J, Ti, Tj. Should I just call it T1, T2?
So every edge comes with two matrices.
Every edge basically comes with two
Two
matrices.
matrices and two vectors.
Two matrices, two vectors. Notice this is that's the constraint basically, and gap C is 2 to 2 games. F2L is defined accordingly. Notice this is exactly the 4-cycle form that I said.
And the alphabet here is F2 to the N.
F2 to the L. The alphabet is Albert size. And basically, the theorem which they proved is the following. M-1. One. For all epsilon. Notice out here you could expect perfect completeness. UG, there's a reason why we couldn't do perfect. You can't expect perfect. And here you could, but they don't prove perfect completeness. That's in fact an open this one. What they prove is for all epsilon and 0, 1, there exists L large enough such that gap 1 minus epsilon 2 to 2 F2L is NP under order n to the poly 1 over epsilon time. That's the key theorem. And notice these are actually 4 cycles because for a given there are exactly 2 values, you can get 2 values and this given. It's a 4 cycle, and this is exactly, and this is a theorem we'll prove. And notice, let's see some quick corollaries of this. Is the statement of the theorem clear? We're going to prove this very specific problem is actually NP-hard, and the running time is going to take n3. Notice this can be converted to an UG instance easily. Just replace each of the instances. You have one instance which says it can be equal to V1 or V2. Replace it with one equation that says just V1, equation V2. You're going to an UG instance will satisfy half of that. So immediately you will get out of this a corollary that for all epsilon,
Half plus epsilon.
for 0, 1, there exists L or rather sigma, which is like the sigma, which is the sigma, such that gap half minus epsilon ULC is NP. And in fact, this can be made, that half minus epsilon can be made half. Exactly half. In fact, that's one of the 3 papers listed in the project, potential projects.
It is which one?
I think it's the 3rd one on the list. It's called gap. There's half in the title itself. Half in the title, half UG or something. So they meant here, by the way, here if we had got perfect completeness, that half would have been trivial. We don't know how to do that yet. What we know is here, the corollary from here to here, in the corollary, we know how to make this into half. This is Amai and Bashko, the subsequent result they know how to. But there's an immediate corollary of this. And the point is, this corollary refutes all the objections that are coming from the Aurora-Barak spiral. The Aurora-Barak spiral, everything, all the objections that they gave held not only for UG, but also for this version of UG. But this is now actually, it's a theorem, it's NP hard. All the objections they had for UG not being true, were also not true for half UG not being true. But half UG is NP hard.
So for any half satisfiable instance, they output an epsilon represents.
The epsilon, they take time to the end to the epsilon prime. And if that epsilon prime, so it's a question of that reduction running time.
Both there as well as epsilon makes it like epsilon.
Yeah, it doesn't give you anything because it goes over 2 power n. So because the n to the poly 1 over epsilon, the running time of the algorithm is 2 to the n to the epsilon. The n now here is n to the poly 1 over epsilon. So now if you put these two together, if it goes more than 2 power n, it's utterly meaningless. So basically that's what's happening there. Their epsilon prime. So the question is this: all that possibly their algorithm is right. So what is it? They give you an algorithm which is epsilon prime, epsilon going to 0. And possibly you cannot do this. That is, if you can't make this, you can't make that 2 to the n to the epsilon prime an algorithm which runs better than that. That epsilon prime will be going, because the reduction is running in time, taking time n to the 1 over epsilon. So suppose it was n to the 1 over epsilon, not n to the 1. All that is stating that epsilon prime cannot be smaller than epsilon.
Cannot be larger.
Cannot be smaller than epsilon. If it was smaller, you get a reduction. The epsilon prime that they get here cannot be smaller than epsilon.
If it's smaller, you get a reduction.
You get a reduction that is less than 2 power n. So right now the composition of this polytime reduction and their algorithm together, question is it giving you something like a less than 2 power n algorithm? Does it violate ETH or something for SAT? It doesn't. Current state of affairs don't.
No, but why was Aurora spiral an objection to the hardness of the half? Usually version.
No, the belief was that because of the epsilon prime, the people did not at this point of time believe that the reduction would actually, you would be proving NP hard this way. That is, they thought that when you prove NP hardness, you will prove a statement like MR.
MR.
Most towards RAS. It will give you a nearly linear time reduction.
Okay, but the instances generated here are huge.
The instances generated are huge.
So if you apply that algorithm, you get 2 10.
You get more
But
than.
if this reduction actually ran in fixed poly time or
But
epsilon in the exponent.
But that their algorithm rules. Their algorithm says that algorithm cannot run in fixed polynomial. That is true. It says if such a statement has to be true, it has to be the reduction has to run in time n to the n to the 1 over epsilon prime, whatever their epsilon prime, and it runs in n to the poly 1 over epsilon. Okay. So this was sort of the reason why So it might, so ABS and UG being NP hard can coexist. So you might have, for example, you could expect a similar theorem for UG of the same type, and that can completely coexist with ABS. Now this also tells you, now there's this whole thing about we have not been able to come up with hard instances for UG or 2 to 2 things. But now once you have an NP hard reduction, suppose you have an NP hard reduction for a particular problem, say some problem P, we have an NP hard reduction from SAT. That means if you take a hard instance for SAT and move and undergo the reduction, you are going to get a hard instance for the problem P. But this is also true for integrality gap instance. Suppose I give an integrality gap instance for SAT and I apply the reduction to it. The instance which I get here is an integrality gap instance, or rather, if I give you a distribution of instances for SAT for which I know algorithms don't work, and those distributions I run this reduction on, and I get now a distribution of instances for P. That's in principle a hard distribution for this. In principle, for both 2UG and 2 to 2 games, we can come up with a distribution now, which is basically take the distribution for SAT or pre-lin or whatever, wherever you're starting this, apply the reduction. This seems like an extremely unnatural way of coming up with a hard distribution of hard instances. But you are able to, so the previous thing that they don't exist instances, we are able to now, at least for 2UG, half UG, we do have a distribution of instances. And that just comes once you have a reduction, you have a distribution for a problem. Once you have a reduction from A to B, if you have hard instances for A, they naturally translate to hard instances for B by applying the reduction. Okay. So even the other sort of objection, lack of this theorem, of course, when you have proved a theorem, it's going to counter all facts that why the theorem is false. Okay. So these are sort of in the high level, it's up to almost UG, it's going to 2 to 2. UG would have been 1 to 1, and they may manage today to do 2 to 2. But there are also consequences for this, for hardness of approximation, the consequences for inapproximability. There are a couple of them. I state the two most important ones. First is to vertex cover. So vertex cover, we saw that if UG were true, you get a 2, there is 2 minus epsilon is hard. What you get now is for all epsilon in 0, all epsilon. Into 1. Root 2 into 1 minus epsilon. Approximation of vertex cover. It's NP. So basically, do the same reduction which we did, but starting from not UG but 2 to 2, you get this. So I might try to do this in one of the modules. I'll try to see starting from the 2 to 2, can we get square root 2? We previously started from UG and got 2. From 2 to 2, do you get square root 2? This might be one of the things, depending, we'll spend most of the time trying to prove 2 to 2. If I have time, I'll also go to proving this particular corollary. How many necessary? It's up to us. But I plan to finish. I will not go any more than next Friday. So that's for UG. Then for graph coloring. So graph coloring, So we know to check if the graph is three colorable, this is LP hard. Now you can ask, suppose I give you a three colorable graph, what's the minimum number of colors you can color it with? Efficient. Yeah, I promised you it's a three colorable graph. Basically, you want to distinguish three colorable graph. So NP hardness says it's NP hard to distinguish between graphs which are which require three colors, which require at most three colors, and which require at least four colors. That's what NP hardness is. Now I want to say three versus I want to find the largest M such that I can distinguish between graphs which are three colorable and require at least M colors. Fortunately, the whole machinery of PCP does not really help you for this particular problem. For this particular problem, the current best known is we can distinguish graphs which are three colorable from graphs which are five colorable. It goes one better than the usual NP hardness. That's where the state of art stops. I'd like to push this a little more. For
How much? So at what point do we have efficient algorithm?
efficient algorithms, terrible. Efficient algorithms take a three colorable graph and color it with n to the power c colors, where c is 0.199999.
That is correct.
It's not n colors. So, and this has been a whole body of work. There's this Victorson's Avi's thesis is basically getting the n to square root n was his thesis. Then there have been semi-definite programming, Kagar, Motwani, Sudan got the square root n to a smaller number. And then it's a mixture of both the combinatorial, this one. The state of art is n to the 0.1999.
Avi gave an algorithm.
We gave an algorithm. It's actually a very simple algorithm. So graph coloring, given a three colorable graph, state of art colors it with n to the 0.19999 things. So in particular, you must be able to show, if that is the best thing that we can do, you must be able to show that a three colorable graph should be distinguishable by a 1,000 colorable graph. That is, you must show that it's NP hard to distinguish these two.
Is it possible to distinguish between three versions?
Three versus, no, it's hard. It's hard. Distinguishing these two is hard. So I want to show how much can I widen the gap and still prove it is hard. We don't yet know how to do this. Whereas the 3 versus n to the 0.1999 is what is easy. That's what we can distinguish. So the question is, this is a completely graph coloring for in the world of inner programming. This is probably one of the most embarrassing things out here for graphs.
And the question of coloring and three colorable graphs is whatever polylog and all those things are a natural algorithm effect.
So yeah. No, people are trying to look at basic. No, you should look at the progress. And the exponent is like n to the power 0.199 is the current this one. The exponent like the fourth decimal, the fifth, there have been algorithms which are just improved on the fourth decimal and the exponential management. Each of them is a stock Fox paper. This is actually it's the area which we just don't understand, both from the upper side and from
recent papers, right?
since they have end of the 0.199 is a few years ago. It's just before the pandemic. And so it's not very long.
Who did it?
So the earlier papers were Kargar, Blum, Sudan, Kargar, Motwani, Sudan. This was immediately after Gomez Williamson came. Now the most all of these use SDP. And not just SDP, they use higher levels of LSR.
So they are not combinatorial or
so actually it's even more annoying than that. They don't just use SDP. They will run an SDP, they'll run a combinatorial algorithm, and they'll take the best of the two. And the analysis says the best of the two gets this. They don't know how to show. So it's in some sense, it tells you it's not the right algorithm. But we don't know what to do about it. That's the state of it. So I keep forgetting. Ichi Kawarabayashi. This is Japanese.
This is
Kenichi Kawarabayashi. Oh, no, it's last 4 years. Kenichi Kawarabayashi is and Mike Torup also. So they have a bunch of such things. Okay, so graph coloring, you would like to distinguish this. So what you can show over here, this is a result of Dinur, Mossel and Regev. So reggae, but then was reggae Smith concept. I don't think was. They know most of reggae. They show that is well before the 2 to 2. This is a paper from about 15 years ago. They show that if this type of label curve with these sort of 2 to 2 constraints are hard, then it's hard to distinguish NP hard. Now it is NP hard because this was now NP hard. NP hard still doesn't solve the problem between graphs which are almost 4 colorable for on M and graphs So what they managed to show is it's NP hard. They started from the 2 to 2 3. Now the 2 to 2 is NP hard. You can show that it's NP hard to distinguish graphs which are almost 4 colorable. What do I mean by that? You drop off an epsilon fraction of the vertices, then the graph is 4 colorable. And graphs whose largest independent set is of size at most epsilon, which will the consequence of that will be the chromatic number is at least 1 over epsilon. They managed to show this. So this is now that we still don't know how to separate 3. 3 the best is 5 currently, but 4 not even 4, it's not exactly 4. It's almost 4, and any large number we can show this.
Have people looked at like sub-exponential time algorithms, quasi-exponential graph with and the epsilon colors?
Yeah, but I don't think we have any better. So this is an area which requires things, but we don't have things of doing it. The graph coloring, it seems to suggest one. And how, if you want to improve these results, now you would want to actually, if you want their reductions to go through, you would want that sigma to epsilon relation, you will need tighter relationships. Okay. It will be interesting to do this for 3 color data. By the way, things are a little better if you go to hypergraphs. That is not graphs, but hypergraphs, and ask for coloring. Then
What? How large?
even if you go, so even starting off with, I think the current best. So you can go. I think the current best result is Girish. Girish's cases. I think he gets 8 uniform hypergraphs, which you can't distinguish 2 colorable 8 uniform hypergraphs from 8 uniform hypergraphs, which require at least n to the power sound. And sorry, 2 to the power log n to the power 1 minus epsilon. It's not polynomial, but it's almost polynomial. So this we know how to do, but this doesn't need UG or any of this. It requires standard PCP machinery. From that we can prove this. Well, the question is with UG, can you do more better? Okay. So that's where we are. So what are we going to do in the rest of this module? We'll try to prove the 2 to 2 theorem. theorem and see the first application if time permits. And what we are going to do the rest of today's lecture, I'll sort of give an overview of how the 2-to-2 theorem is proved. And then we'll leave some theorems in the subparts, which we will prove in the subsequent lectures. Okay, so proof of the 2-to-2. Means our starting point for this will not be SAT, but will be gap 3 then. Will be gap 1 minus epsilon. We have, of course, half plus epsilon, but I think I need only 3/4 gap 3 then. That will be our starting. This we already know how to prove NP hardness. There will be some requirement on how small epsilon should be. That will come out later on. That will be our starting point. Okay. We are now going to then.
So these are arity 3 linear equations over.
These are arity 3. So this is basically of the form xi plus xj plus xk equals bunch of such constraints. So what are we going? So how is the, and from that we are going to come to a 2-to-2. This one. So how are we going to do this? It's going to have two very similar parts. We are now going to, from gap 3 limb, we'll construct an outer object. We'll construct an outer object. We'll do that shortly. Construct an outer object, and then that outer object. So previously we had an outer thing which was label cover, and then each inner part, each of them, we encoded using the long code. And this was, we went to the specific problem. Now we have the specific. Now, the specific problem we want to prove is gap 2-to-2 games. So for that, we will construct a potential outer problem, which we will get by applying parallel repetition on this. I'll do that in a second. What's the outer problem? We'll get an outer problem on this. The nice thing will be all the constraints to be checked will be linear constraints. It will be a fully linear problem, but it's because we are lost in perfect completeness. And because of this starting point, we would lose perfect completeness throughout the whole thing. That is, it will be good if you can get something with perfect completeness for the 2-to-2 theorem. We don't know that because of the starting point. And we don't know how to do this. And you'll see this. We need the constraints to be linear at every single place for this reduction to work. So we'll come up with an outer object. And then the outer object we're going to encode using what's called the Grassmann code. We'll define what this is. The Grassmann code will have the nice feature that it will have a 2-to-2 property. So we'll have to first define the outer object. The Grassmann code, we'll have to analyze the Grassmann code just like we analyze a long code. And then we have to show that the composition works. So there are 3 parts to this proof. The outer object, which we'll describe in its entirety right now. Then we'll have to talk about the Grassmann code. We'll have to just talk about why the Grassmann code, this one. That's one whole result of its own. And then how to compose this Grassmann code with, I'll tell you what is the composition, but then we'll have to prove that the composition actually works. That's going to be the one. And what is the so let's talk about the outer PCP from gap 3. Okay, before I go, why am I going to do all of this? Eventually, it's going, you want to get a 2-to-2 constraint. So, how many 2-to-2 constraints are there? So, what we are going to do is, so the reason we are working with we're going to work with all our solutions will be linear equation. Everything is going to be linear equation. So instead of giving a linear, so I want a particular linear function, I'll ask, give me the linear function on an L-dimensional space. Give me the entirety of a linear function on an L-dimensional space. So eventually the proofs will be this one. Every object, every node will refer to some L-dimensional space or some other space. And we'll ask, give me the restriction of some global function on this L-dimensional space. And that will be one query. One query will be asking a particular L-dimensional space and asking what's the restriction of some function to this L-dimensional space. Another query will also be another L-dimensional space, and you'll ask this one. Now you're going to check consistency between these. In the natural way, you want this to be 2 to 2. So any L-dimensional thing over here, so you'll ensure that these two L-dimensional spaces you check actually have an L-1 dimension intersection, so that they are talking about the same function. And all you're going to check is that on the intersection they agree, so that they both have two possibilities to, and that's where the 2 to 2 is going to come. So that's going to be the basic idea. You're going to eventually be talking about the final, all these solutions will all be linear equations on various things. You're going to ask the linear equations restricted to L-dimensional subspaces. And then the test will be of the form, compare two L-dimensional subspaces whose intersection is L-1. That obviously has a 2 to 2 feature to it. That's where the 2 to 2 is going to come. Question is, how do we do this whole? So what's the outer object? The outer object, the way we are going to construct the outer object is, we are going to pick, from this object, I'm going to construct another outer object which has U and V. And edges between the two. And what is each element of U? How do I pick an object? So let K be some number such that.
So here you're given a fixed relation.
I'm given a K3 relation, that's a starting point. From that, I'm going to convert it to this. Then there will be the Grassmann code. So this will be the bipartite sort of label code I'm going to have, and each of them I'm going to expand using the Grassmann code, which will ensure the 2 to 2 property. This will not have 2 to 2. This is just
Grassmann code replaces long code.
It's going to replace long code. This is going to replace label code. Grassmann code is going to have. Grassmann code will be such that any test connects will automatically be 2 to 2, and then we'll have to do the composition of this. So now I need to describe this object here. How am I going to describe? So there's going to be a parameter K floating, and K is such that K times epsilon is strictly still smaller than 1. And you will see this why. Basically, what we are going to do is we want the completeness still to be maintained. We are going to we're going to take each vertex on the left is going to represent K constraints of the 3 lim constraints. We want them all to be simultaneously satisfied. Therefore, the error will be from 1 minus epsilon become 1 minus K epsilon. We still want that to be a small number. So pick K random equations. Motor field, let's call this instance psi equations. E1, E2, EK. So, okay. And each thing over here is going to be E1, E2, EK. Okay. And then there's going to be some parameters floating. There's a parameter K, there's a parameter beta. And for each I in K, we'll do the following. AI is going to be EI with probability 1 minus beta. I'm going to now, this is going to be a tuple A1 to AK. And what is the A1 to AK? With 1 minus beta probability, it's going to be the whole equation itself. Otherwise, it will be a random variable in EI with probability beta. So with So either you give the entire equation, AI, EI, or you pick one of the variables that participate in the three and just give that one.
So another spelling distribution over.
So I'm now describing the whole edge structure of this. And that's
What is the randomness over any probability?
I'm just telling you how this graph was being generated. It's a weighted graph.
Okay.
The weighted graph, and that's the graph. When are the edges between them? I'm putting the weight on the edges. I'm describing this label cover instance. Okay. And we can assume with high probability that, and let u be the number of variables. So this is u be the number of variables in E1 to EK, and v the number of variables in A1 to AK. Okay. We're going to think of K, N. So N and M are very large. So gap 3 lim, this is once again it's N variables, M equations. There are going to be several, in this proof, there are going to be several things. N and M are the things that are going off to infinity. K and L are now constants. They will be constants which go to infinity at a much slower rate. Just like in the long code thing, also the alphabet was a size K that was independent of the ambient alphabet N, which was, then there was another, there were various orders of infinity. Various things are going to infinity at different rates. So N and M, think of them this one. K is a fixed constant. It will also slowly go to infinity, but it's a constant that depends on epsilon. It's a fixed constant. If you want epsilon small enough, you choose K to be suitably large. Now, K is going to be constant in terms of N. Therefore, U typically, size of U is going, U is typically going, sorry, U is the variables. The size of U typically will be, for most cases, will be like 3K. It will exactly involve 3K variables. And size of B will be roughly 3K minus 2 beta K. Is that right?
So 3K because you're going to pick them infinity.
I'm going to pick them
in order to say.
They probably
K
are
is
small.
small.
K constant, N and M are large. The other one is 3K. Beta K of them are expected to become a collapsive variable. And for each of them, you remove 2 beta K. And we'll assume, and what we will do is, if U and V are not of this size or around this size, we will drop off that edge. With Chernoff bounds, you'll know that most of the vertex edges are going to be concentrated only around this. So there'll be a small league. We'll do that.
Okay, so this reduction is randomized. It takes the
This one, it's not randomized.
picking EI is probably.
No, that's just tells you the weight of every edge.
Okay.
Just. You exhaustively do it, that's it.
So you do that and you covariance will deviate far.
Yeah. And so now here, what is this one going to be? What's the label set going to be? So now the edges are of this type between EIs and AIs.
So your reduction is running in time roughly M to the K.
M to the K, and that's exactly where the
And K times epsilon is the one, so K is about
1 over epsilon. That's the place where it's going to be poly 1 over. That's exactly the only place. In fact, no, there's one other place, but in fact, no, that's the only place where N is going to 1 over epsilon. There'll be another place that get multiplied by 2 to the power 1 over epsilon, but M is going to 1 over epsilon precisely because of this. It's exactly this place where it's going to happen. Okay.
Right.
We pause for finally one. Okay. So instead of thinking of these guys as E1 to EK, we'll think of it as U comma E1 to EK. It's this tuple. It's U which is setting the which are the variables that are participating in them, and E1 to EK are the K equations constraint that are satisfying. Here I will just specify V. I will drop this whole thing and I'll just specify V. So in some sense, it's U, a vector of constraints, and every edge looks like this. Edge in. Let's call this graph G. And what's the variable? What's the assignment I'm going to give? So this guy is going to get labeled from a string in F2 to the U. This guy is going to get labeled from a string in F2 to the V. Basically, I'm going to give a 3K bit assignment here and a 3K minus 2 beta K assignment here. And you need to check two things. Firstly, this assignment is a projection of this, and furthermore that. So what are you going to check? You're going to give me an A over here. Sorry, let's call it A. Let's call it alpha over here and a beta over here. These are the labels. And what is the consistency test? First, the alpha satisfies all linear equations in E bar. That's the first thing. And beta is a projection of alpha. That's going to be the. So let's call this. Let's call this whole thing. Let's call this phi. I want to claim. So we have a reduction now from psi to phi. Psi to phi. This was gap 3, then gap 1 minus epsilon 3/4 3 then. And this was what shall we call it? Just call it.
Soundness will change.
Huh? Yeah, so I'll just write a theorem that will capture the completeness and soundness. Let's just call this problem label cover. Gap label cover. And the proposition is above is a reduction from gap 1 minus epsilon 3/4 3 ln 2 to gap. I have to tell what the completeness and soundness are. This one I want to claim it's 1 minus k epsilon. The completeness is 1 minus k epsilon. And soundness, how do we prove soundness? Notice that this is essentially as if you're doing like a parallel repetition. If I had given just the variables and the clauses, if I dropped off all the variables, so there are beta k of the variables, beta k of the constraints, I'm doing only one variable. So for beta k of them, there's parallel repetition going on over there. Therefore, I claim that this is essentially 2 power minus omega beta k LC. Because the underlying problem has at least there's a constant gap for the single version of the problem. You're repeating it beta k times. There's this beta k parallel repetition sitting inside it. Therefore, it should be at least LC is that problem which I described.
They're saying only consider those equations for which we drop we need not drop out the variables. Contribute
Just that will,
contribute this.
this one, just that should have already this. Therefore, this is certainly you know that this problem, it has completeness 1 minus k epsilon, soundness 2 power minus omega beta k.
And beta is constant.
Beta is a constant. Beta, so epsilon, so the way it goes, the 2 power minus omega beta k will eventually be the soundness that we are going to get. It will be the eventual soundness of the gap 2, or actually even small, it will be even from a function smaller than this. So you will now have to choose beta k, so that beta k is number. So the there will be a whole bunch of, you will have to reverse engineer each of these variables as we'll see all of this. So that's the first of the, that's the outermost object. And the crucial thing is alpha satisfies only linear equations. There's only linear equations you have to check. Therefore, what we will now do is the following. Now I'm going to talk about what I'm going to call the Grassmann code. I'll first just tell the Grassmann code, not do anything on it. Compose it, and then state the two big theorems that we need to do eventually. What is Grassmann? So even we have to talk about the Grassmann in the context of the outer guy, but let's talk about it first independently.
How did you get to the minus beta k? So there's a value equation on what?
On so essentially,
So how many rounds are there repeated? K round.
exactly beta k rounds. Those are the number of guys for which there is a.
Okay. That's the game you're beating.
That's the game I'm looking. So a single variable, there's a variable, there's an equation variable game being played, and that's being repeated beta k times. So there's that inner that game is sitting inside this.
Yeah.
Okay, you have to win at least that way. So that's the. I'm not going to prove this, but this is essentially from what we have this. Okay. So what's the Grassmann? The Grassmann is so. We're going to talk about, suppose I want to encode this string x in f2 to the k. This k is actually either going to be 3k or it's going to be 3k minus 2 beta. This k is what was 3k or 3k. So I want to encode this string. How am I going to encode this string? In the long code, we took this and we took the string and we encoded we write the dictator corresponding to the string. Now, what we will do is, because eventually we also need to check that x satisfies these certain linear constraints. That's this one. So, in order to keep that this one, we don't need to go to the long code. The reason we went to the long code is sometimes there we had to check arbitrary nonlinear constraints, and that's why long code let us do all those nonlinear constraints. Here you have only linear constraints. So, first thing which we'll do is we'll encode this using the Hadamard encoding. We'll go to the function. We will go to the function f of x, which is f2k to f2, which is a natural function which takes any variable z to x in a product. It's this linear function. So given any x, we can go to this corresponding linear function f of x. I could encode it by this object. I could give, but I haven't taken. But now what I will further do is the Grassmann code, what I will do, instead of giving this linear function as a truth table, you gave it as every location you gave it. We will give this linear function not for every location, but so we'll take for each. So there will be yet another for every L, such that L is a subspace of F2K. And dimension of L is small l. We will give the restriction fx of L. So fx will be a function from what we call, this is KL2 to F2N. So what is this shorthand for? Usually, if I put square brackets, this is all sets of size. This is all L size sets of this one K. This is all L dimensional subspaces of this ambient K dimensional subspace, but we're working in GF2. So for every subspace, I am going to give you what is the restriction of this function. That restriction of the function is also a linear function. It requires only n bits to represent it. Therefore, I can represent it as f2 to the n.
So here you will take any basis of the subspace and give the evaluation.
So yeah, so this is just some way of identifying it. So essentially, it's f2 to the n. And I'm going to think of this as it's going to give me a linear function on the space. There is some way of indexing the 2 power n linear functions, and I'm telling you which of the linear functions I'm giving you. So that's how I'm going to encode a particular string x. A string x of f2 to the k is going to be encoded this way. The point is, eventually we will have to check that the string satisfies certain linear constraints. We have to fold, but because everything over here is linear, that folding will be easy to handle later.
What should we think of the parameters? What is little L compared?
So the various things. So k was a constant, but now k is also going to go slowly to infinity. Little L is going to be much smaller than k. So at this point, in the previous discussion, n and m were infinity, k was a constant. At this point, k is going to infinity, little L is going to be small constant in terms of, and we are going to have these levels of infinity over here. Each one is going at a different order too. So basically, in the usual Hadamard code, Hadamard encoding of f of x, in the past we have done by point, we gave it at every point, we gave the restriction of the linear function at that point. Now instead of every point, I'm going to do it for every L dimensional subspace. I'm going to give the restriction of the linear space to that L dimensional subspace.
So this is that's like a 0-dimensional version.
That's like in the affine word, that's the affine Grassmannian. This is only giving on linear spaces. I'm not giving. You could have done this on affine spaces also. They do it only for linear spaces. Yeah. So this is affine Grassmannian, this is fit on the Grassmannian will refer to, Grassmannian refers to things in which you have an ambient, there's a finite field, possibly there's not even a finite, there's a field, there's an ambient dimension, and you're talking about all subspaces of a particular dimension. Now we need to now test that this object is a. So this is how we are going to. So we are going to be given. Basically, we are going to be given for each u. In the previous thing, we are going to be given an fu going from 3k L choose 2 to f2L, and similarly for each, this is u and u, and for each v and v, we're going to be given fv, which is going from size of v L to f2 to v. That's how they are going to blow up. This is like the long coding, and I need to conduct a test between them. But forget about the test between them. Let's first ask, if I give you, must first ask even more preliminary question. Given f from k choose L2 to f2L. So here k will choose 2 refers to all L-dimensional subspaces f2k. Technically speaking, it doesn't refer to all L, it refers to the number of L-dimensional subspaces. But just like I'm just going to use it for, that's an indexing way of doing it here. Given I want to test if this is an encoding of an x in f2 to the k are equivalently is it a restriction of a linear function? So what we are now given is for every n-dimensional subspace, we are given a linear function. What we want to ask, do these all group together from a single linear function over the entire space, the k dimension?
Going to robust test.
Yeah, we now have to come up with a test for this. So what are potential tests? That's going to be the, actually one whole paper is trying to analyze this particular. We'll come up with a candidate test. We have to go and look at it. So let's do that. So what I will do in the rest of the this one is we'll come up with a candidate test which is not going to be useful for us. It won't be 2 to 2. Then we'll modify it to make it 2 to 2. And that will show that it has terrible counterexamples to the statement we want to prove. So we'll only be able to prove some weak version of the statement, and then we'll have to say why that weak version of the statement is sufficient to complete the proof. Okay, so let's start with the test that we can. So let's call this the test Grassmann intersection B. So I'm going to design a test for this. So the input is a function f.
What is
Huh? A L F2. It's going to be
so that's S, then B.
which is this
Test, what is the subscript of
Grassmann GR.
GR, comma?
B, there's going to be, we'll see what B is. B is going to be a parameter. I need to do this test, and this is given as an oracle. The natural test is, one natural test is pick L prime, both in KL choose to, two L-dimensional subspaces. Such that, but you want some consistency, such that the dimension of L intersection L prime is B. That B is, so B is that object. Okay, I call it P in our discussion. So let's stick to T here for intersections on the server. So if F L restricted to L intersection L prime is the same linear function as F L prime restricted to L intersection L prime. Okay. We'd like to this. For this test, it's not hard to modify our existing. So we know the Fourier analysis for the Hadamard thing. You can sort of adapt that to this and prove the following theorem. It's not too hard to do this.
I think it's like line point, the
Huh?
plain line point.
This is even more, it's just Fourier analysis just for. This is a BLR test. A little more than this, we can prove the following theorem. Hmm? Suppose probability test GRT accepts is greater than delta. Notice we are always working in this very small regime. It's not in the 1 minus delta regime. Then there exists a global linear function so this is capital F such that probability when I pick a random L, F restricted to L is identical to F restricted to L is at least omega delta Q, provided 1 less than or equal to T less than L by 4 and delta is greater than 6 times 2 power T by 4. So this does say that actually you do get something. That is it. You want to check whether this one. So natural thing is to pick two guys. Obviously, you want them to have some intersection. So you want to test consistency. Check them. Have guys, two guys which have intersection T, and check them against each other. And this is not hard. It's an adaptation of the BLR proof, but you can prove this. So this is very much in the direction which we would like to do. Because we're going from this one. Unfortunate thing is this test? What is this test? Is it it's a D to D test or what? What sort of test is it?
It's called L minus a lot.
It's a 2 power L minus T to 2 power L minus T test. So if you want it to be a 2 to 2 test, you have to make T goes to 1. T go to L minus 1. 2 go to L minus 1. Now let's look at the statement of the theorem and see if it's
Sorry, delta there is 6 over 2 to the T over 4.
sorry, T.
So B is T. The T less than L by 4 constant is considered.
Yeah, so two things. Firstly, this test works only when the intersection is not too large, and on the other hand, the intersection is not too small. If you want for a particular delta, this puts a lower bound on. So you need the intersection to be at least this size and at most this size. That is, the intersection should be bounded away from 1, and the intersection should be constant fraction away from. It should be some L. It should be some L by 10 or L by here L by 4. So this is not what we want. This yields a this yields a 2 to the T minus L minus T 2 to the L minus T test. We want T to be L minus 1, but then the theorem doesn't hold. we're going to now modify this test. The test we want to study is this. We want to talk about, let's call this. We want to call this linear. There's a special case when this dimension is L minus 1. That's the test I want to look at. And I want to ask, can I analyze this? And so what I would like to prove, the question which I would like to ask is the following such statement true.
The linear query complexity will be high.
Why?
If a dimension is large, checking 1 by L fraction, 1 by Q fraction of the points.
No, I'm not going. I'm going to, for every L dimensional thing, there is a vertex. That vertex is going to tell me what's a linear function.
Okay, so the alphabet size is.
The alphabet size is large. I don't care about the alphabet size. Alphabet size. In fact, the alphabet size is exactly F2 to the L.
Okay, that is the.
That is the L that is eventually going to come in our this one. So the question which I would like to ask is the following: for all delta, does there exist an epsilon such that the following, such that if probability test GR ln, this is the accepts greater than delta, then there exists a global linear function f, so that probability n is these steps. I want to ask is this true? And more importantly, how am I going to state the parameters? This epsilon and delta should be fixed constants, but that for all L and K this holds. It should go, order of this one should go this way. That's the order I want to do.
So you want, so later you would want L and K to increase.
L and K to increase, yeah.
So that's why.
Yeah.
And epsilon is something that will be dictated by whatever the initial epsilon.
The epsilon is fine. The final epsilon is going to come from what? So there will be a, just like in the norm code analysis, you move from a delta to 4 delta square or something, that's this delta to epsilon square. That will be the soundness of the final soundness. So for that, you have to choose a large enough k. These are all going to go upward. Let's even ask such a statement true. And I want to say there are, the reason the previous theorem didn't handle this, there are glaring counterexamples to such a. So how are we going to come up with this counterexample? So let's look at the following. Let's focus our attention to let's take a particular direction, and let's take all linear subspaces that contain this particular direction.
So, okay, so the counterexample there is you really want to come up with a function f such that in one corner it passes the test because of some values written in a corner, and you don't want a global.
I don't want a global thing. Yeah. Okay. So how am I going to come up? So take this is not going to come up with that whatever example. It's not going to satisfy your example. What I say right away will not. We'll have to modify it. Let's take all sub L dimensional subspaces that contain a particular fixed direction. So extremely small fraction of the entire space. What is the fraction
So
of
it's 1/f or 1/.
What is it, 1/f? It's all L-dimensional subspaces that contain a particular direction.
So you've lost 1 degree of freedom.
I've lost 1 degree of freedom. So suppose it was instead of the Grassmannian, it was the Johnson graph. So what is the Grassmannian? Grassmannian is there's an ambient K-dimensional subspace and you're looking at L-dimensional subspaces. Those are your vertices. The Johnson is there are K distinct elements in the universe and you're looking at subsets of size L.
K-1 to Z-1 by K.
It's K-1 choose L-1 by K choose L. How large is this? It is exactly L by K. It's exactly L by K. And here I'm going to think of L as very small compared to K. And a similar thing is going to happen over here. Here it will be, the ratio will be the number of L-1 dimensional subspaces in a K-1 dimensional subspace by L dimensional subspaces in K dimension. You can write this down, but this will also, it's not going to be L by K, but it's going to go, you can show that if L is a fixed constant and K is the one going to infinity, this is going to be insignificantly small. It's not even delta fraction. It's going to be insignificantly small fraction. But, so this is an extremely tiny fraction of the space. But notice, when I fix to these L dimensional spaces, I can put the number, if you pick a random L prime dimensional subspace that has intersection L-1 with this, most of them are also going to contain this direction. Very few of them are not going to escape this. So this, in fact, in some set, if you draw this graph in which the vertices are the L-dimensional subspaces and edges are between two L-dimensional subspaces which intersect on an L-1 dimensional subspace, this set which I have given you is an extremely non-expanding set. In fact, with probability half, it stays inside. It's only with probability half where the edges go out. This is a direction. Now, you might say that this is not a solution because the test is not. So,
The test is not like
the test is not passing with delta population. I just choose another direction and give up another set. So, for this set, I could just pick an arbitrary linear function, and for this, so what have I pick a particular direction? I pick all the linear subspaces that contain that direction, and I pick an arbitrary linear function, and just over here I answer based on this arbitrary linear function. And you know for everything, given the first element L, if you have picked from this space, you're going to satisfy with probability half. Of course, the probability that you pick the first element is very, very small.
you're going to get enough.
I'm going to pick enough of them. I'm going to pick another direction. I'm going to pick another direction. Pick 2 to the L directions. I pick enough of them so that these are more or less disjoint. Each one of them, they are disjoint spaces. They together cover delta fraction of the entire universe.
So what if one subspace contains 2 directions? What if one?
I can do all of that. I'm just coming up with a counterexample right now. So the counterexample is this following counterexample. Basically, the counterexample exists to the fact that there exists this really, really tiny sized set which is non-expanding in this graph. So let's look at this graph, which I'm going to call, let's consider the graph. Consider this graph is called Grassmannian KL. Its vertices are it's this natural graph which we talk about, and edges are L prime is an edge. If dimension of L intersection L prime is equal to L minus 1. Sometimes we more generally study Grassmannian KLP, which is the same thing. The vertex is the same thing, it's just that L prime is an edge. If dimension of L intersection prime is 2. We'll sometimes consider this. Most times we consider only the GRKL. point is this graph has really tiny sets that are non-expanding. What is our example? Let's consider fix a direction. It's a direction. Say V. And that's SV is set of all L such that V belongs to L. Aim, there are other observations that SP is a non-expanding set. More particular, phi of SV, that is the number of edges between SV and complement of SV versus the degree of the graph times size of SV. That's the conductance. That, by the way, this graph is a regular graph. It's a perfectly regular graph. And that's the degree of this graph. This I'm claiming is roughly half.
Expanding would be close to 1.
Huh?
Expanding would be close to 1.
Expander means expander will
Close to D.
close to no. D is in the denominator.
Close to.
All I'm claiming is expander will be close to 1. Yeah. So half probability is staying inside. Half probability is staying inside. And now I want to claim that you can actually, okay, SV is not a counterexample. So if I take SV and label SV by an arbitrary linear function, that's not a counterexample because SV is insignificantly small. But I want to claim that I can collect several SVs, which are basically, I can collect disjoint copies of S, several such V's and take the union of them. And they will together have this property. Because each of them acts independently. So this will be a counterexample to our whole this one. In fact, there can exist more general counterexample. Any set collection of SVs such that one pairwise disjoint two here union is a delta fraction of KL2 will serve as a counterexample to the conjecture.
How can two SVs be disjoint? They will always exist a subspace which contains.
Yeah, what you will say, they will always exist because the origin is going to be contained in this one. You will show that each SV will actually have constant fraction of guys
Not outside.
outside it. And that's good enough. That is each SV you will put this. Okay, I can't I should put this almost. Have a almost.
Not just already, I mean, you give two directions, I can always find a subspace.
Yeah. So what we're going to do this is we are more generally I'm going to construct S of A comma B. So I'm going to more generally we're going to look at A and B are going to be two subspaces. A, B are subspaces. Of dimension A and codimension B. And A is a subset of B. So suppose I take two subspaces A such that A plus B is less than or equal to R. So in pictorially it looks like this. There is the vector space V. There's A over here. It's a constant dimension space, and then there's a B over there. So B is B's codimension is small, A's dimension is small, that together, think of R as a small number. This one, and I'm going to def SAB is going to be set of all L such that A is a subset, L subset. So you are taking 2, I'm going to take R guys and put thing. But I can also do it from the other end. I can take the subspaces which are orthogonal to a particular set of directions. That's what codimension is talking about. And I claim that as long as these sets SAB, they're all non-expanding sets. For all, take SABs for AB such that R is a constant. These will all be non-expanding sets. It's very likely that their neighbor will. What should happen for their? If you pick an L in this, what's the property that the L prime does it? That the direction you are throwing out, the direction you are throwing out should not the direction you are throwing out a direction and you are adding a direction. The direction you are adding should also be in A, and the direction you are throwing out, sorry. The direction you're adding should be in B, and the direction you're throwing out one. If you get both of these, this one, then you will satisfy this. And this happens with probability 1 minus 1 over 2 to the R. You're actually making it even better. So, in fact, the non-expanding thing is becoming even better and better. This is going to be even more non-expanding than this. With high probability are going to go inside. So, all these SABs are actually going to, and then you can collect build SABs which are union of these or almost union of these. And this will be a counterexample to the question. Be careful. We are not going to be able to prove this. So at best, what we can prove is the following theorem. For all delta, there exists an epsilon and an integer r such that for all sufficiently large L and A larger than L, let S belong to the vertex set of Grassmannian KL such that P of S is less than or equal to delta. That it is a non-expanding set. I want to, so right now, what have we shown? We have given examples of things which are non-expanding. Now, this theorem is going to say these are the only sort of non-expanding sets. So give me any set yes which is non-expanding. In this, sorry, this is a subset. Then there exists subspaces A subset of B such that dimension of A plus codimension of B is less than or equal to R such that the relative density of S intersection SAB is at least that is, even though S is this one, once you focus on this particular SAB, yes, looks like a large fraction. So it sort of says those counterexamples are the only sort of counterexamples. This might be a tiny part of the space, but every counterexample I give you, I want to say there is I've shown you that these are counterexamples. I want to say that for every counterexample, there is a tiny part of the space which is sort of stating why this is the counterexample. So this is, by the way, this was the final theorem proved by KMS. The last of the KMS 2 papers, they showed this. This is the result in KMS2. We write two other theorems, both of which then DKKMS what it had proven was actually said it stated this as a conjecture and showed what was assuming this as a conjecture, it had proven what we want for the test. So it proves the following result. It proves that for all delta, there exists an epsilon and an integer r such that for sufficiently large LK, if f is a function from capital F, if f function from KL to F to L is sitting here, satisfies probability L prime L intersection L prime. Just let me just say probability that test Grassmannian len F accepts is at least delta, then there exists A subspace B such that dimension of A plus 4-dimension of B less than or equal to R and a global linear function F such that probability. Now I'm not going to pick an L completely. What I would like to show is the following. F restricted to L is actually this is at least epsilon. I won't be able to prove this for arbitrary, but if I pick an L in A and B, I'll be able to. This theorem from the previous theorem is a triviality. We'll just say it's like a 3-line argument. What did DKKMS1 do? DKKMS1 showed how to compose this with the outer guy to get this one. KMS1 laid the whole plan. So that was the way things went out. So we'll have to prove 3 theorems. We'll have to first prove this theorem. I'm not sure if I'll go in this order. I have to prove this theorem. From this theorem, I'll have to prove this. These both will go in the same this one. And then we'll have to use this to compose and finish. To compose this Grassmann test with outer object. Okay. Final cap 2 to 2 game systems. Class. So what I will possibly do in the next lecture will be we'll focus more on this composition. We'll go into the composition, see how it composes, finish that part, and then the subsequent lecture we will do KMS2. And we still have energy, we will go from there to vertex cover or okay. Presentation will be the week after. Not the next day. So it will be so this is the first week, second week, the third week of May. on the Friday.